Let's see if we have any attendees. Uh, We have people joining in. Hi, everyone. Good morning to people on this side of the world, and good evening to the other side,
Yeah.
and whatever's in between.
What time is it yours? It's 11 o'clock in your
11 a.m. Yeah.
yeah.
Hi, Scott. Good evening. Scott is joined from. Scott, where are you putting up from? Portland, USA.
Oh.
Nice to meet. Nice to have you, Scott. And we have a few more people. Hi guys, please just join in the chat. We'd love to know where are you guys joining from? What time is it at your place? Thanks for attending, and that's really nice to have you all here. "4:30 p.m. in Australia." Hi Murray, thanks for joining. I hope I'm pronouncing your name right. We'll just wait for about 5-7 minutes till more people just join in, and we'll begin. Sounds good?
That sounds fine.
Meanwhile, I'll just put up a story on Instagram as well. I think you're not very active on Instagram, Richard, are you?
Am I what? I'm sorry.
You're not very active on social media, are you?
No, I'm not. No, it's I have had to deal with social media for a while. I'm just one of those guys, and part of it has to do with, I'm sure, my age group, and that I have a Facebook account, I have an Instagram account that I never use, stuff like that. I don't really have a particular reason at this stage of life to do that or need that, and it's okay, and I'm fine with it. It's really not.
That's good. People our age are just consumed by it, to be honest.
Yeah, and it would be very easy to get consumed by it. So it's life is out there, and that's where I try to exist. So
yeah, makes sense. Pablo has joined from Child. Is that how you pronounce it? I hope I'm not wrong. 2:30 a.m. Wow, that's some serious. Sorry.
That's dedication.
Yeah, that's dedication.
So, welcome.
Hi, Nils joins from Sweden. Good morning.
Very good.
Just a couple more minutes. I'll be just making up some posts, and we should be off to go. We have about 10 people joining in so far. So
good.
That's good. That's really good.
Yeah, you want to go ahead and get started then?
Yeah, sure. I'm just posting a link and we'll be off.
Sounds good.
Okay, so let's go ahead with the webinar. Thanks for joining in, guys. It's really great to have you all here. And um, I'll just start with introducing Richard, and Richard doesn't need any introduction, to be honest. We all know his experience with bass trapping and low frequency control, the fusion laboratory testing. I don't know, like, if there's any major studio out there, especially in the USA, that does not imply the membrane traps or diffusion control, especially the way Richard has developed, right? Recently, I've been seeing a lot of projects that involve RealAcoustix panels for scattering and all of that. But more than all of career highlights of Richard and all the amazing things that he's done, um, even though I don't know much about him so far, it's been only a few months that I've got to know about him, got in touch with him. He's really a very fantastic guy to hang around. And last time I said this for someone, it was Sam last webinar. If there's somebody, if some of you have attended that webinar, and these two people, I'm really, you could just say that I'm outright a fan of these two people, because the way they share their experience, their knowledge, without any bias, without any sales agenda, it's just amazing. And I don't need to talk about it. It's just, you'll just see it through the course of this webinar. But yeah, on the screen that you can read about Richard's experience, some of the really crazy projects that he's been involved with. Come on, guys, like Jimi Hendrix, Capitol Records. These are some serious names, right? So yeah, hopefully you guys already know that. But Richard is great, a super fun guy to hang around, impressive career, and impressive work that he's done through the years.
Yep. Well, thank
So
you. Yeah.
yeah, so going forward, this session we'll be covering with low frequency control. This is the session overview that you can see on your screens. Mostly we'll be talking about how low frequencies behave in a room. And part of it is already covered in the podcast that we did with Richard about a week ago. So I hope you guys have already watched it. And if you haven't, maybe after the webinar, if you watch it, it will help clear out some basics. But nevertheless, we'll be establishing some fundamentals, some foundations on it briefly in the webinar. Then we'll move on to our hero section, or the actual deal of this webinar. We'll be talking about different low frequency treatment mechanisms, especially about the membranes. There's a whole dedicated section on it. And Richard has a really amazing presentation that he did with ASTM and ASA, both of them, right? I guess.
ASTM. It was an ASA presentation primarily. So yeah, when about 2 years ago, I gave this presentation at ASA talking about, and primarily it was about the testing and developing a testing methodology for that gives us accurate information about bass traps and how they perform.
Yeah, so that's a very interesting. I mean, I think we gave a bit of spoilers in that in podcast as well, but I got to see it later. About a couple of days ago, Richard showed that presentation to me, and that's a really interesting presentation about how Richard and Ron Saro in NWA Labs executed all the testing, some different ways of different way to approach bass traps, membranes in the room. That's really interesting. We'll just take a look at that. And after then, if you guys are still hooked and if time permits, we'll be moving towards a more design-oriented section. Then we'll talk about how Richard approaches the way to control low frequencies in different sorts of environments, be it small rooms like studios or large format venues like concert halls or something. Probably we'll pull up some case studies and show you guys the before and afters. And of course, there will be a deep and elaborate Q&A session in the end.
Okay.
So yeah, let's just start with low frequency control in rooms, right? So Richard, I'll just ask you the same question that we started our podcast with. And also just a disclaimer as to you guys as well. This webinar is going to be more like a podcast, because Richard and I were discussing again that rather than going through like a presentation, Richard feels much more comfortable and much more enjoyable if I ask all the questions and make it like a conversational thing. So I hope you guys won't get bored too much of hearing me, but I'll keep myself to a minimum. And please keep asking your questions in the chat as well, whether you're attending on YouTube or the Riverside. Your questions will be visible to me all the time. So whatever's relevant in between through the flow of this presentation, I'll ask your questions along to Richard as well. Or if something's not very relevant to the present conversation, we'll be sure to take up in the end. So moving forward, Richard, I'll ask the same question that I started the podcast with. what's the deal with these low frequencies? Why are they so hard to control, and why this is the most misunderstood subject in studio acoustics?
Well, I think it's not only misunderstood; it's also the most problematic for so many people that are designing rooms. And most of the time we're talking about recording studios. I mean, I've done everything from rooms that can barely hold 4 people to 7 to 10,000 population concert halls, but you take a different approach doing that. So what we're talking about here is primarily going to be small to medium sized rooms that typically control rooms in a studio. And I think that's kind of, if we stay in that box, it'll be a much easier conversation, obviously, because there's a lot of different places we could go with low frequency control. And really that's what it's all about, is trying to control the large wavelengths that happen. And we're talking things below 100 hertz, and those and going down is as far as and there's, in this day and age, in the last 20 years, that has actually gone lower and lower and lower with regards to what we need to control and how we need to control. But if we take the large wavelengths and the huge spread, I mean, take like a 40 hertz signal, for instance. 40 hertz is about 28 feet long. It's longer than most control rooms are, for sure. And so, but so you think, well, I'm not getting that full, I don't get that full wavelength. You don't have to have the full wave. You can do half waves, 4/4 waves, things like that. And you still have 40 hertz, populating all over the place. And the problem that people always have with low frequencies is they're huge. You take a 10K, and it's a very small, very focused wavelength. And they've always had problems getting horns to actually spread it enough, or tweeters, or whatever the case might be. Not so much with subwoofers. You put a subwoofer in, and all of a sudden your entire room is being populated by a tremendous amount of wavelength. Now, the one thing that you have to be aware of is that depending on the design of the room, and most people are aware of this, there's certainly been programs out for some time, and calculations for how to, when you create a room that's X width and Y length and so much height, you can pretty much calculate fairly easily what that what the frequency that's going to be problematic in the room is going to be. Doesn't always work, by the way, because a lot of times there are appurtenances, stuff in the way that can change that can actually change how those low frequencies, and especially the one that's most problematic. We talk about a Schroeder frequency. You've got that mentioned here. The Schroeder frequency is really just the passover point, as I call it. It's the point where we go from being in a velocity based to a low frequency basis, where we're really getting more in the room.
Right.
And and I'll show this a little bit later in that presentation. When when I started to do this, and everything that I've done over the last almost 20 years of having RealAcoustix and being involved with that, and creating that company, was to try to solve problems for people. That's what an acoustics company should do, in my opinion. And we didn't see that happening a lot, and a lot of information that people have been passing around for the last 50 years. And I say that because I'm old enough to know that, is that they will say, hey, my product does this, but he or she doesn't have any proof of that, because there is technically, whether it's ISO or whether it's ASTM, there is no low frequency test data that is approved by either one of those testing organizations. So here, this was one of the things that I had to deal with, and I'm a member of ASTM and have been for many years. And 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 we have people that, many labs, reverberation chambers that, and in some cases, some impedance tubes as well. I am not a fan of impedance tubes, especially for low frequency testing. And I could go into that at length, but I'm not going to. I prefer rooms that actually are rooms that actually have some character as it would be in the real world. And that's why a reverb chamber is a little closer. Although, reverb chambers have their own problems. I own one. I made one, and I actually have a fairly large reverb chamber, and it's it's proved helpful, but they still have their the problems, whether it's ISO 354 or ASTM C423. They still have some problems with trying to figure out how to make this perfect. And you would think after 100 years they should have had that, but they don't. So it is what it is. But given those wavelengths, so what people have been doing for the longest time is they have been the guys who want to go off the books, so to speak, and in terms of testing, have been putting multiple in the modal zones. One thing that's right about what was right about it is that they were putting devices in the corners of a room. The problem is that every one of them, and I know a great many people that have reverb chambers and then do it for a business and things like that, they would group a bunch of devices in two corners of the room and take a test in the modal response, which was, if you know anything about reverb chambers, everything from 1 meter, from the walls to 1 meter is it's no man's land, so to speak, in a reverb chamber. The diffuse field, which is the field that everybody in a reverb chamber wants to use, it doesn't start until 1 meter away from the walls. Well, when you're talking about low frequencies, you're talking about things that populate against the walls and again in corners. And so consequently, you can't test a low frequency device in the diffuse field of a reverb chamber. Just doesn't work. And yet we have, there's lots of data out there and people that are selling products that say, hey, I've done this A mount in the diffuse field of this reverb chamber, and here's my results. Well, the results are useless because that is not an appropriate way to do it. That's not where these devices are used. They are used in the modal field, and the modal field is against the walls and in corners. So, there's kind of the problem that began. And so when I started to look at this, and we had some bass trapping, but nothing too dramatic until about 5, 6 years ago, when I started. And I had made bass traps for clients like Sam Burkow and people like that, knowing, how to, but they were always one-offs. They were not, it wasn't a product that we were selling. It was something I did, for that client. And to good results, because I knew how to do it. But it was, the test data, the tested methodology was not perfected. I was treating, and they were diaphragmatic ones, and I was treating them more like a drum. It's just basically tuning it like you would, a drum essentially, and it's or a timpani, as it were. And so I started to look at this real seriously, and went to, Ron Sorrow and I have been friends for more years than I can like to mention, and his lab it's no longer, his lab is no longer in existence, but his lab was the largest one in the United States that was a commercial lab and was qualified down to 20 hertz. So I went to him, I said, look, I want to test, but I don't want to test the way you've been doing it. I want to start separating these devices so that they are not, they are not coupled together, so that we don't get performance that is illegitimate. I want to know what the individual product itself is doing, and that's so we took the same principles as, say, a C423 in terms of the square footage, based on the room itself. And in his particular case, it was 120 square feet. And then we took, basically from that point, we had to experiment a lot. I mean, it was over a 2-year period, and 3 different test, times, that to finally come up with the right way to do it, and over 100, almost 200 devices, and in experimentation and all that, and came up with a methodology, and again, I'll show that to you in a little while. But the methodology was really interesting, because once we came up with it, it really showed us that, again, part of the great part about it and the bad part about it was that, it's an NRC, and noise reduction coefficient. Well, in ASTM terms, an NRC should not exceed 1. But a lot of people think that 1 is perfect absorption. It's not. A 1 is more around 6 dB, give or take, 6 to 7 dB. And that kind of threw people off, because that's that 0 to 1. We're getting 1.8s, 1.9s in our bass trap. But the reason for that, it's a very finite frequency. It's or a range of frequencies depending on how we do it. And so, the trick, and what I wanted to come up with, was a methodology for creating specific frequencies, because that's what I get. The level of clients that we had were such that, hey, I've got a problem at 72 hertz, and I need to get rid of that. I don't care about anything else in the room, but this 72 hertz is killing me, And so now my goal was to create something where I could actually tune the device, to whatever the client needed. And if he needed something a little more broadband, to create that as well. That was trickier, honestly, than creating the single frequency. So, that's, doing that. And again, most people, it's funny, most people don't have a hard time figuring out where their problem is, because most programs, whether you're using REW or Smart or, any of the other programs that are out there, most programs can tell you where your problem is. It's, that's a fairly, do an impulse response, and you can find exactly what you need to find and where the problem is. So that was never the issue. The issue was solving the problem. And that's where, I came up with a methodology of how to do that, and how to, create something that's, that will solve the individual problems. And it's, it's interesting to me that nobody in the industry, I mean, and I know companies that have been around for 50, 60 years, I was a relative newbie. I started my company in 2008, and, but it seemed to me a logical thing to do, to try to create a device that will really perform where somebody needs it to perform. So that's, and, as far as the concentration of zones in a room, again, that's a test. That's a fairly easy test. It's not really that hard to know. And, people will ask questions, and you and I have even talked about it, about what, what's the downside? Is there a downside to a diaphragmatic, resonant bass trap? And yeah, I mean, there's going to be downsides to everything to some extent. It's what happened there? The reflective behavior and re-radiation, as you have it stipulated there. That is, I tend to look at it as no different than having a wall. Because these devices are specific. If you look at it just as having a wall, then you can control the rest of those behaviors with velocity-based treatments, whether it be, a 2-inch fiberglass panel, or mineral wool, or, the million different other ways of doing it. And some people will say, well, hey, I've got a problem down at 50 hertz, and I'm gonna take and I'm gonna put a hole on either side of the back of the room, and I'm gonna stuff it. The hole's gonna be 8 feet deep, and I'm gonna stuff it with fiberglass, and that will solve the problem. No, it doesn't solve the problem, because your problem is specific. Your answer is broadband, and when you start to do something like that, and you create a broadband, you now affect many other things that are going to create more problems. So it's the reason I came up with doing this as a diaphragmatic. Now diaphragmatics are not easy. It's one of the things that I discovered in going about doing it is that if as a manufacturer, if we're going to do this, every component in the device has to be exactly the same as the component that we tested. And in this case, the diaphragm has to be consistent, whoever we use, because a lot of times you'll find people, and well, I'm going to go to this metal shop and get my diaphragmatic sheet there, and that may not be the same, and having a diaphragm difference of even a tenth of a millimeter makes a difference in terms of how it performs. Not to mention all the interior damping and things like that that take place. So there's you've got that tuning frequency that everybody's relying on the company to provide is finite, and it has to be exactly what they want, or else they're not going to achieve their results that they want. So it gets interesting, and you start doing all of this stuff and realizing, oh, what have I created? I've got now I've got to make sure this happens. So
Yeah, since you're already in the specifics about membrane, so would you just establish the working principle about this for the audience that maybe need to membranes? If we can just establish a working principle about how the mechanism of membranes work and why they are required. I mean, like what makes them different? What are the problems that they're targeting that a simple broadband problem cannot solve? Like we were talking about the Schroeder frequency, you mentioned about the transitioning stage. What kind
sure.
of problems dominate the room in that range that makes the membrane the only solution? And what is the mechanism that they operate on? If you can just shed some light on that.
Well, the mechanics of it, without giving away too much, obviously, but because I have some, I sold RealAcoustix a couple of years ago, so I have to be very careful. Yeah, but the mechanics of it are fairly straightforward. Like I said, I was creating these before custom for people, and I look at it like I look at a tunable drum. It's anybody that's familiar with drums, especially timpani, and the timpanis can be tuned fairly easily, as the drum head can be, but in this case, it's a sealed box. And that sealed box and what's inside of it, which I can't talk about, but what's inside of it dampens it. So the difference between a drum and this is that it does not have a tone of its own. If you hit it with a mallet or something like that, it's just thud. You're not going to hear anything. And that's very important. It cannot have any factors, either some frequency factor of its own that it produces. It has to be damped enough to be able to absorb that frequency, but not make a sound or anything like that. So and I experimented a lot with tunings, coming from I come from the music industry originally, building speaker cabinets and I had lived in Las Vegas for the good portion of my life, and had a large PA company and things like that, and I was designing speakers for myself and for other people, and so I come from that world, understanding how tunings work and that, and it's but this was entirely different because I experimented actually with tuning them, and having them have some air relief and things like that. Ultimately, that did not work. And that was, and the reason it didn't is because the minute you start allowing it to breathe, you lose all your effectiveness of the unit. So so we have and unlike a lot of other companies who would have one, maybe two bass traps, they might have a corner trap and a flat trap. I ended up with 20 different designs, and those can be manipulated from there depending on the frequency that you want, and that's and or the bandwidth that you want. Because that was another experiment, and that I had to end up doing, because some people didn't want it to be very specific. They didn't want a bandwidth that looks like this. They might want something that looks more like this. And to get it broadband like that was even more interesting, for lack of a better word, to do. And so all of the physical properties of it still has to be a sealed device. Ultimately, after a year of messing around with porting and various other things, figured that just doesn't work. It just doesn't work. And and again, that application came really from my experience with building speaker cabinets and designing speakers for PA systems and things like that. And so all of this was trial. There was a lot of trials with it. I felt like Edison at some point, where how many times can you put the light bulb in and see if it works? But ultimately we got it to work, and got the thing. You talk about edge effect and mounting. The mounting of the units is important. It is one of those things. Ultimately, the best mounting methods for any of these. Now, the corner units are really a lot simpler, because you just put them in the corner. They have no edges to speak of, because the edges are parallel, or with the sides. But when you come to flat traps, obviously it's a four-sided box, and you have to be aware that you could potentially be creating some other anomalies by the use of it in a where you put it. And so I always suggest to people, if you can, to make it flush to the wall. It's not always going to be able to do that. People aren't always going to be able to do that, and it's not huge. I mean, the problem, it doesn't create a huge problem ultimately. It solves more problems than it creates. And because mostly you can usually have at least the back and the two sides, two of the sides tied into some form of the building itself. So that tends to be okay. But again, it's basically how I came up with that, and how we ultimately created all these different devices. Like I said, it made it difficult as a manufacturer. It made it difficult because we have all these different models, but you have to have them in order to really give the client what they need. Whatever the designer or the acoustician, whomever it might be, to give them what they need, you have to have that. A bass trap cannot be a singular device and say, hey, this solves all your problems. It doesn't. It has to be designed for that.
Yeah, and also I think it's worth mentioning that the data that we're comparing here about other companies, it's just for like educational insights. Just so it doesn't get misread. It's not about any kind of plugins for any promotion, because Richard doesn't even own the company anymore. He's retired. Yeah, so it's just about because some of you who have been part of my WhatsApp group may have remembered the incident that happened a few years ago, that we were discussing about some X companies, bass traps, and all that. A lot of mess happened, because that's what happens, because a lot of companies sell bass traps with corner foams and rock wool, but they're not essentially bass traps. They're just broadband absorbers positioned in very high bass concentration areas. That Richard will also just show what these bass concentration regions are in a room in this presentation later on. But yeah, that's what we're comparing data on, that what bass traps actually are and how they work. So Richard, since you were mentioning about it, that you just mentioned a subtle thing, that there's some anomalies caused by bass traps, membrane traps, if not positioned correctly or if not designed correctly. So even though they're not that much worse, but what sort of anomaly should one expect when they are just dealing with membranes? If you could shed some light on that.
Well, again, I think with anything where you have a reflective surface as well. I mean, it's obviously absorptive at a certain frequency, but it's reflective otherwise. You do have to be careful about how you put your other because most of the reflections are going to be above the 100 hertz. That's the great majority of those reflections. So most of that can easily be resolved with velocity based absorption, and or diffusion, as the case might be. And then I have a fairly strong reputation as a diffuser designer as well. And and you and I were talking about this the other day, that how much I told you how much diffusers can solve mid-low frequency problems. And like if you look at the ones, it's an RQS 450 that I designed. And I designed in my time with RealAcoustix, I designed 25 different quadratic residue diffusers that do all kinds of different things, and they're really quite incredible to in resolving low frequency problems. But when I say low frequency, we're talking not below 80. It's going to be 80 to 125, in that range, and can be very for that. At the same time, also providing a diffuse environment, which is a whole nother subject I won't get into. But the so that's one way to resolve it. Again, you can put on sides and things like that. You can put fiberglass panel, any number of different types of panels. I have preferences, obviously, and as anybody does, when you start dealing with this stuff and you've been designing rooms for as long as I've been designing rooms, I have preferences. Everybody has their preferences as to what they do, but it's it is one of those things where that's fairly easily resolved. You and I talked the other day about can a bass trap, a diaphragmatic bass trap like ours, be covered with a panel? Well, you can't. The one thing you can't do is you cannot affect the diaphragmatic surface itself. That has to be left alone, and it cannot be impeded by any number of different things. You can put a light fabric over it, for instance. If a lot of people want to put fabric over it, and that's fine. That's not a big. It's not going to change things on it. But when it comes to like putting you had the question about putting fiberglass over it. Well, the only way you can do that is if for instance, you could use 1-inch fiberglass, 6-pound fiberglass, but it has to be offset by about 1 inch around the edges. No more than a 1-inch edge. You could offset, put a trim around it, 1-inch trim around it, and then put the panel on, as long as there's a 1-inch airspace. And as long as you don't glue the fabric onto the front, you can glue the fabric onto the sides. These are little things that, the company would tell you, if you wanted to know, but that information is really important because the low frequencies will still pass through that. Now, if you get into a 2-inch, it starts to become a problem because it's a lot of surface area for that in velocity to pass through, even at those frequencies. So it's not like those frequencies are not disturbed by that. So 1-inch I have found doesn't really affect it too much. 2-inch, it's going to be a problem. And again, so that if you wanted to have something that's going to absorb higher frequencies, and in the case of a 1-inch panel, you're looking at typically something that starts around 100 hertz, 125 hertz, depending on it, and goes up from there. And so you can absorb the high frequencies and still control the low frequencies by doing that. So it's another way to do that.
Right. We have a question from Maurice Ingleton. For interesting room modes, is the placement important? Surface area, I'm assuming relates to more absorption. That's a good question.
Yeah, the surface area, obviously creates more absorption. It's interesting when we talk about, again, I made certain assumptions when I first started designing these things, as to, the bigger I make it, with the depth won't make any difference. If I make the plate bigger, I'm going to get a lower frequency response, which was false. So it didn't work that way. And I got shot down, by my own, predilections, ideas about what it would do. The nice thing is that we were able to make units. The largest unit we make is 4x4, or 4 feet by 4 feet, and it's and it makes it really nice from a standpoint of fitting into most places. And we have smaller units than that still get down. Those things can affect the frequency, obviously, but it really is not an issue of having to have this huge amount of space, because these things are very, very efficient. That's the one thing, compared to, like, when you compare it to a velocity based device, like if you take a typical, like I said, a 1-inch or a 2-inch fiberglass or mineral wool panel, that are going to, that's going to give you, good efficacy from maybe 100, 125, depending on the thickness, up to 6-7K, easily. This is really specific, and when you get into bass traps, it's diaphragmatic bass traps, it's very specific. And I don't really worry about the reflection of the rest of it too much, because again, you can surround it, you can do various things to absorb those other frequencies that might otherwise be impeded. And again, when you talk about testing in rooms, you're always going to find that there's a group of frequencies in a very specific area, or a single frequency in a very specific area, that your room responds in, and that's causing the problems in the room. And that's what it's there. That's why it has to be specific. That's why it's, the design of it is so important, because, and again, we do have some models. I say we, I don't know the company anymore, but we have some models. I designed models that have broader cues, so the cue isn't so tight. It can actually go across maybe a quarter to a half an octave. And we can center it where it needs to be. And that's really important as well, because there are rooms that create that. You never quite know everything your room's going to do. I've always found that no matter what, somebody will come back after they've designed the room and they've planned everything, and they go, I got this problem. And it's always in the low frequencies. It's always under 100 hertz. And it's, it's just the nature of the beast. No matter how much we think we can take math and make it, make it populate properly, it doesn't always work that way. So that's my feeling about it.
Yeah, and also, since you mentioned about the question about Murray's question about surface area and how you explain it, this works. I've personally, like, we've been building some rigid membranes in our projects, and we've been using a fair amount of limp membranes as well. So, do you have any conflicting experiences with using limp membranes versus rigid membranes? Would you like to share some anomalies between the two of them?
My experience with limp membranes, and I've seen it done with mass loaded vinyl and a bunch of other things. It's and I've had experience with that. There's nothing wrong with them if that's what you're looking to absorb. If you feel that you have a problem, because that's going to be much more broadband.
Right. With the very less absorption coefficient.
Right. Yeah. And it doesn't have, they typically don't have the absorption coefficients that something like the BASSMOD has. The coefficients are going to be in the one area.
Less than one.
Yeah. So it's which is fine. There's nothing wrong with a mass, something like that. But again, its efficacy is not, is not what I was trying to achieve. And we've done bass traps with, with mass loaded vinyl and some other products to create that. I know when we had a smaller product for not quite as low of frequencies as something that the BASSMODs will do, but for mid-low, something from 80 to 125, something in that area. Again, done with a limp diaphragm as opposed to a hard diaphragm, and those so that they could be modular in the sense of helping to control a broader area, but not, they couldn't go as low as the other other types like our diaphragmatics could. So yeah. So it's yeah, I mean, everything has its purpose, and you just have to know, and you as an acoustician, you go, oh hey, I've got this problem, and it's a weird problem, and and maybe that limp mass unit is exactly what it needs. That's great. That's the one thing that people don't understand. I mean, like, I used to get I used to get a lot of heat for the fact that I had 25 different diffusers, that I designed. And I said, well, I can show you 25 different rooms where each one of these one would serve better than the other. And same thing applies to the bass traps. It's, this one size fits all stuff is ridiculous. It's just not the reality. It's, every room is different. Every room has its its needs, and what's going to make it sound the best. And it's and that should be our objective always, is to try to find the best materials for the room, this specific room that you're doing, and make sure that it fits the application.
Makes sense. Makes sense. Let's talk about position and orientation, Richard. And we already have a question from Murray about that. So hopefully, Murray, your question will be answered in this segment, but please feel free to rephrase it if something else. So, Richard, you have talked about a lot about how positioning and orientation of membranes differ, especially in the way you have tested it. Could you please share how that translates while putting these into a real room? Like when you're putting in one corner or say on the ceiling, how does flipping it over or putting it on the floor facing upwards change the way it behaves, acting to gravity or whatnot?
Yeah, I think a lot of times that is really decided by what the room, is. There's, I've found so many times where the room itself really determines how the design is made. Because we had, I designed corner units and flat units, specifically for the fact that we're going to have different applications and different places where the corners may not be available. A lot of designs now do various things to corners and ceilings and stuff like that. I'm not a big fan of bass traps in ceilings, because I think it's probably the least advisable location for it. One of the things that I suggest with bass traps is that and this would apply to any bass trap, is that whatever is propagating the bass, in this case, subwoofers primarily, whatever is propagating it, you need to put it in as not close necessarily, but you need to put it as in line, as an axial reflection would be, as in line with it as you can. So if you have, two subwoofers on each side of a room and they're facing the back of the room, try to line them up as much as possible with the back of the room, or put corner units in, because they'll solve the problems. Low frequencies themselves tend to propagate in corners, and they tend to roll. They just want to do this. So You know, corners are always, you know, probably one of the best places to have them. And you can use flat traps or you can use corner traps. Either way, it will work. But the you know, in some of the, if you'd used a corner trap, if you use one of the corner BASSMODs, for instance, you do have an advantage of getting, if you wanted, getting some additional bandwidth on it, because it's capable of actually dealing with more bandwidth than a flat trap can. But again, that, you know, that your determination of that will depend on what your testing tells you and what you're, you know, what you're going to see when you finally look at the units and say, okay, because invariably bass traps are one of the last things to go in the room. You know, it always seems to be the case. So it's and that's mostly because you don't quite know for sure exactly what's going to, where the problems are going to be. So but you know, the orientations should be relevant to where the essentially the initial signal is coming from. So, you know, and I've seen a lot of, we did one just before I left. We did a room that was, and actually it was a listening room for a guy, and he was using, I mean, this guy spent $1 million on this room, and it was crazy. It was, I mean, he had 2 woofers in the back that were 60 inches woofers. 60, you know, think about that. Okay, it's a huge, you had two woofers, and they were back facing, you know, so facing, you know, they were in the rear of the room. And then he had a series of 18-inch woofers on the sides of the room. And he's going, how should we do this? And it's like one of those things where I go, I don't know.
16 inches woofer, like what kind of room is that?
It was a listening room for, I think he had a video, you know, screen in it as well. But, you know, I mean, you know, he was going to blow his ears out, I think. You know, I don't know what he was trying to do with it. Yeah, I mean, you know, it was, I mean, the cells for the 6-foot woofers were 2 feet of concrete all the way around. And, you know, it was, you know, it was way over the top. I mean, obviously this is a room that, you know, nobody will ever see because it's, yeah, but it's, you know, it was one of those things where, you know, I don't even know how much, you know, how much we could provide in a bass trap, you know, or sets of bass traps to control this room. You know, obviously it was out of control in a sense, just from the design itself. But, you know, that's neither here nor there. But like I said, you know, a lot of it's going to depend, you know, if you really pay attention to where the propagation source is of the low frequencies, you can pretty much determine where you're going to need to put the bass traps as well.
Yeah, makes sense. And moving forward, Richard, you've tested bass traps in a lab. You've made your own measurements. You've tested in one of the greatest labs on earth to be existed, and you've put these bass traps in real studios. Have you noticed any deviations from the previously calculated predictions to the lab test and then to the real world data of how they perform?
Yeah, I mean, a lot of times we'll see, you know, we'll see differences in the calculations of, you know, of what the, you know, what the acoustician or whoever came up with, and saying, okay, you know, this is, I'm going to have, you know, I'm going to have a hump at, you know, 63 hertz. Okay, so, you know, they use that and say, you know, based on whatever, you know, again, if they're using ease or Odeon or something else, they can give you those kinds of, you know, math calculations. Quite often, though, it does end up being a little bit different. And you know, that's, like I said, when they can give us a call. And fortunately, the design systems that I came up with allow us to address that and say, okay, I'm going to, you know, I need to have this, and we can give them that center frequency, or we can give them a more broadband set of frequencies, if the room is talking, and when I use that terminology specifically, if if the room is talking a little bit too much in whatever frequency band it might be in the low frequency, and it's always in the low frequencies. There's once in a while you get stuff in the high frequencies, but that can easily be addressed with velocity based materials.
Yeah, makes sense. Um, all right, so I think we've covered most of the membranes part, and hopefully that should have established a good base of how membranes and in general base control works in a room. We've talked about how these are the working principle, the design parameters, placements, base mods, and we've talked about the downsides of using membranes and how you should deal with that. There's
Right.
a few more remaining that might discuss, but before we move forward, and I think it's a good time to talk about testing and presenting the presentation that you have, Richard, about the ASTM, the one that you presented with ASTM. But before moving
Sure.
forward, guys, if you have any questions around the already discussed concepts, please feel free to just type in the chat. Or if you need a break as well, if it's already too much, because I understand it's a very technical webinar. We don't generally do these deeply technical ones. So if you need a break of 5 minutes, we can do that as well. Just let us know in the chat.
Is everybody good?
We have a question from James. Does the modal response shift with resonant traps similar to adding fiber traps?
Does the modal response shift with resonant traps?
Let me show it up again.
Yeah,
Sorry.
adding similar to adding fiber traps. Not really. We don't. It's not an additive process. I mean, it's a very finite device in that sense. We're not adding or subtracting. I mean, if you need to add more, if there's, if for instance a particular device isn't enough for the room, you're still in the same frequency range, but then you add another diaphragmatic trap, it's still going to be the same frequency. That doesn't change. The one thing we know about that is because of the way that they perform. So if you need more, and it's very seldom that happens because these are so efficient. Again, the typical BASSMOD performance is somewhere around an NRC of 1.5, which is really quite heavy. I mean, you don't see that in any velocity test. I mean, this is something that's very unique to this particular device. And so, you find that, a couple of the small devices like this in the right place will typically solve most problems. And, my whole perspective, in my lifetime, I've owned 3 studios, and, my personal perspective of this is that we're always trying to make a room where I don't have to use equalization. And that's my mantra. It was always my mantra with my studios, whether I was designing a speaker system for it or whether I was, creating a room, in every different way. I want the room to be as natural as possible without having electronics, try to solve the problem. And, even with all of the wonderful new electronics that we have, I've never been a big fan of trying to equalize a room electronically. I'd rather do it acoustically. And that's, so again, that comes from personal experience. And, that's, I don't think that we, and again, that's going to depend on how you put it in. That's what, so many people I've seen over the decades, literally, trying to resolve problems by, taking an equalizer. And again, we have lots of better things now, but taking an equalizer and trying to resolve problems, all that does is create more problems, because there are so many issues that that people don't realize, or they think if they're using a 3rd octave equalizer and they pull down, 1K, that all they're affecting is 1K. They're not. They're affecting usually about a full octave on either side. Maybe not as much as the center frequency, but it is affecting it. So, those are all things that that's why acoustics are so important in a studio, and the proper design is so important, because it will help prevent you having to, and then you can use your favorite speakers and do all that kind of stuff. And you want your room to be neutral. And I'm talking about control rooms here. Now you talk about recording studios, the part where the musicians are, that's a whole different subject. That needs to have character. The best studios in the world have some, significant characteristics to them, but not control rooms. Control rooms to me need to be flat. They need to be, something, because you have to trust what you're listening to and what you're setting out to the world. So that's.
Yeah, and just like you said, Colin, also this resonates with you that EQ does not fix time domain issues, which is a really important thing to. And I'm really glad that in recent years people have started understanding that, even in the hi-fi world and the producer world. Before that, it was just acousticians yapping about that. No, don't use DSP correction. It's not solving any problems. It just appears to have solved by just skimming down your speakers for compensating the problems that your room is presenting in a later time domain.
Right.
And that's a good thing that people have started realizing it, and we don't have to just constantly criticize these products, even though they are really good at some points, like DSP's correction, EQ's phase correction is really good sometimes for integrating subwoofers and a lot of that kind of stuff, but
Sure.
not for room correction.
Right. Yeah, it shouldn't be used for room correction. Your room should be correct to begin with. Like I say, in an ideal world, we wouldn't have to use any kind of equalization, whether it's really high end digital or something from the past. And there's guys that are stuck on the stuff in the past too. So in certain studios, so it's and yeah, I've seen probably every kind of studio there is in the world, and it's and from the working, it's people ask me about working in Electric Lady. So some, what was it, 2011, I was asked to create 2 new rooms for the first time since 1970 in Electric Lady Studios. And
Electric Lady is Jimi Hendrix, right?
Huh?
Electric Lady is Jimi Hendrix, right?
Yeah, Electric Lady in New York. Yeah, and Jimi Hendrix's studio. So, and it was I mean, it was a great honor to be able to do that. But a lot of people go in, and this studio is highly coveted as being one of the most important studios in the world, especially for rock and roll, and it is. But if you look at John Stork's design, and John's a great guy, but when he designed it in 1970, he was an architect. He wasn't an acoustician, and it's really interesting to me. The design of the room for that time was awesome, but by current standards, it's like, we'd never design a room like that, because it's longer than it is deep, and it's or wider than it is deep, and it's got its back control. It's not much of anything. It's just a few slats of wood and some 2-inch panels or something. But but nobody ever wants to touch it. But there are people that know how to work in it, and that's always one of the things. You and I talked about that the other day. And a studio is only as good as the engineer who understands how to use it. And when you take Eddie, who created all of Jimmy's music and has been creating in that room since the beginning of time, practically, it's he knows the room, and he knows its faults, he knows its weaknesses, and he knows its strengths, and he's able to make it work. He was able to make that work even at that time. Are you talking about the room for Dan Auerbach? I don't know that name, so I apologize. I don't know.
This room is for Jimi Hendrix, Colin, Electric Lady Studios in New York.
Right.
Those are some really pretty great insights. I just can't fathom the fact, how some of the great records that I've grown up listening to, how the journey of these rooms have shaped. I'm just getting to hear firsthand. That's
Yeah,
kind of
yeah.
yeah.
I mean, it's fun. It's enjoyable to me. I mean, I started my life as a musician, so I was listening to Jimmy in 1968 and 69 when before he passed away, and he was one of my favorite musicians, and I loved what Eddie did. Eddie Kramer was a phenomenal engineer and made that work. And John, for the time, created the best studio that was around. But it's just, I think what makes it funny to me is that nobody, and I understand why nobody will ever touch that studio, even though we know it's imperfect. From today's standards, even by John's standards, he would never create a room like that again. But it's there's some things you just never touch. Just some things that life is that way. And it's but I look back at that, and I look at the whole history of studios, and and I'm grateful to be have been around as long as I've been around, and seen as many rooms, and done as many rooms as I have, as to be able to see this stuff. And again, knowing the difference between you've got control rooms and mastering suites, for instance, entirely different rooms, entirely different reasonings for those rooms. And I think that's we've gained all this information, all this and now we're talking 50 plus years, 55 years of of really looking at how we did it. I mean, I'm amazed sometimes when I look back at the rooms that where all this wonderful music in the 50s and 60s was made, and the rooms were terrible. I mean, just absolute. All they were was some tiles put on the wall, and but they were big enough that it really didn't affect them that much. They weren't trying to absorb too much energy or anything like that, and they played a lot softer. Now everything has gotten louder and louder and louder over the years, and so that's what's caused the need to create rooms that have different criteria. And it's been kind of interesting to watch that dialogue, control, and all that stuff over the years. We didn't even think about control rooms in the 50s and 60s. So they were just you went into this room that barely had a couple of small speakers, and it might be at best a 12 inch with a tweeter, and yet you look at the music that was created then. So that's all in the ears of the creator, as they say.
That's great. We have a couple more questions, and just moving on to them. Before, let me just circle back to James' question once again and wrap it up. Uh, as you already answered, that membranes don't really change the way the shift in modal response the way fibers does. And I just let me just present to say my own views on that, and please correct me if I'm wrong. I think the primary reasoning behind this is one, that membranes aren't positioned the way fiber based absorption is positioned in a room. Like the membranes don't cover entire walls, that would just change the room's dimension entirely, or be on the on axis response directly for the speakers, that would lengthen the path for speakers sound energy to travel to the wall and come back to your ears directly. I think that's primarily one of the reasons that why membranes don't change the modal behavior of the room. Or is it something else at work?
No, that's correct. I mean, basically, they don't really, they're very finite. They do exactly what you tell what we say they're going to do, and nothing more, nothing less. And so consequently, it's not going to change much of anything. I mean, there's what you might have some physical changes. In the for instance, if you took a room that had two corners in the back, and then you put corner traps in them, now you've put something that's 45 degrees. So that will change the reflection area of things not related to what the trap is doing, what that bass trap is doing, but it will affect the other frequencies as far as their directionality. That's why I say you have to be aware of that, and you may need to add some velocity based devices to control whatever is being reflected off of the panel that has nothing to do with its performance.
Yeah, that's a really good point. Like putting a membrane in a corner, a diaphragmatic trap in a corner will change the modal behavior of a room, because
Right.
then you're just dealing with the geometry of the room and overall volume of the room. Yeah,
Correct.
that's something worth really noting. Then we have a question from Colin. I'm curious how the placement of traps tuned at different frequency centers is considered when trying to control a wider range of frequency.
Tuned at different frequencies. Well, it's again, some of the designs that I created over time do have we have some that have different frequency centers. Like for instance, I have one that has a 60 hertz and a 63 hertz and a 50 hertz thing, in which some people need that. Some people need that dual frequency. Or I have a couple of others that are wider band, that would cover almost a full octave, not quite, but close to a full octave, and that's going to affect that it's going to be efficient in controlling more problems if you happen to have a more broadband problem in the low frequency areas, which happens. You do find that sometimes where these units are being the rooms themselves have some other, and sometimes it has to do with the sound system, various other things that it's just creating more problems. A lot of times it has to do with the height of the ceiling. There's things like that will do, and that's why I created them. It's just so, hey, if you got this, we can do. And it doesn't mean that we'll necessarily be perfect but we're close enough that we can mitigate most of the problem areas that you might be having. Better than any other solution that's out there. And that's the whole point.
Yeah. I hope that answers your question, Colin. Then we have a really interesting question from Nice. I hope you're pronouncing your name right. Could you expand on the thoughts and experiences on placing pressure-based absorbers for optimizing their performance? And I think that now is a really good time to move to our testing presentation, because that really answers the same question, right? You've elaborated on how spacing and coupled membranes, diaphragmatic traps make a difference. Shall we move to that, Richard?
Sure. Yeah, let me see if I can pull up the presentation.
Right. I'll just stop sharing on my end.
Okay, so let's see.
And Andy, I've noted your question. Just if you could just wait for a while, we'll just be done with this presentation, and I'll take up your question after that.
Okay, and yeah, I always love trying to get this in in Rivers. Well, let's see here. Okay, where did you disappear to? There you go. Okay, so I'm sharing the screen, right? So
yeah, right.
Let's see. Entire screen and I don't know if you're seeing my screen or not, but
not yet.
Yeah, figures. Give me just a second. This is okay. So if I need to switch my screen to this, then don't I? How do I do that? My apologies for.
That's fine. That's fine. Can I help you?
Yeah. No, I can't. Okay, I'm trying to figure out how to get this working. Okay.
You just need to click share screen and on the diagram.
Okay, I found it. Okay, it's just another. This has a lot more buttons. You see that now?
Yeah, it does. Yeah, right. Perfectly.
Okay, cool. Okay, so this is a presentation I gave at ASA a couple of years ago. Test. This is in the test method of how this worked, and the most of this we've talked about. The reverberation chamber testing. This is I like this picture because it kind of walks you through all the different ways we had to test. You know, if you look at the top left corner, it's the diffuse field A mount. This is the way people have been testing for years, and it just doesn't work. Flat out doesn't work. And then the second one right next to it, the modal field corner, is the way that Ron and many other labs were testing low frequencies. But again, coupling these units together gives us false narratives as far as what they're doing. Number three, next to that, is, you know, the first test we did, and we got really weird responses out of these. You know, the next actually four, we got very strange responses. It wasn't until we hit the bottom where it says modal field angled mount that we started to get some efficacy out of it. And ultimately, you know, we found that even having gaps, as you see in that third one from the top, you know, he has a conduit going around there. That conduit, that 3/4 of an inch, gave us a 50 hertz pressure zone that is a false narrative, simply because that pressure was created from behind the unit. Sometimes I've seen people actually use that to their advantage in certain circumstances, but in this case, it was not effective for us. Ultimately, what we ended up with is in the bottom right-hand side was separating these by at least the spacing of the units themselves. So if I had a 4x4 unit, I was going to make sure it was no closer than 4 feet to the, you know, to the next, yeah. And we use the same square footage. Excuse me. We use the same square footage as the typical C423 or ISO 354 would call for, based on the size of the lab, and that seemed to work well, and we got very good results doing that. One of the reasons the results are so much higher than typically is, one, it's in a modal zone, and modal zones are just much hotter, much, you know, is much more significant than the diffuse field. So that was one reason. The other reason is that it's a very limited bandwidth, and it's performing really a lot of information is being thrown at it, and it's only having to deal with so much information. And we found that that's one of the, you know, two of the reasons that we get such, you know, good responses, and they're so much more efficient, which is helpful because you need fewer units in order to accomplish what you need to do. So this is how, you know, when we first started looking at this, we started looking at the eigenmodes for rooms. And in this particular case, you know, something like on the line of a reverb chamber, and this happens to be a reverb chamber that's my size, which is fairly large. And you'll see all the red zones, which are the hottest zones. They're all against the walls. There's a little bit in the centers and some of them, but you can see it's mostly against the walls, which told us that we need to be testing this stuff exactly where they're used. And that's, you know, it's two things. One, you know, two things happened here. With the eigenmodes told us that, you know, we're testing in the right area. And they also told us how much more energy is in that area, which is why we always have problems in the corners of rooms and in the sides of rooms when it comes to low frequencies. So, you know, this was again, a test that was really significant in helping us to determine how to test these things. So, and again, looking at ASTM C423, and we actually did this test. This is a diaphragmatic bass trap I designed, but we're doing it as a typical, and the test was just terrible. It was just, you know, wasn't giving us any proper information at all, knowing what we do know about them. So, and you can see that's the test data. We had a spike at 63 hertz, which, you know, that was fine, but the rest of it was all, it didn't make much sense, to be honest with you. And you know, look at you know, the 40 hertz at a 0.5 and all that, and it, you know, there's something that just didn't ring true, especially as tight as that 63 hertz was. So, then we do this test, and now we, this is how we found out about the, like if you take a look at this one with against the wall. Now this is a thinner trap. It's not the same type of trap, but we have, multiple frequencies here because of that 3/4 inch gap in the back, that 125, and the really in this case a 40 as well, but a 0.5. There were a lot of different things, that it shouldn't be doing, because the bass trap itself should have pretty much a single frequency, might be a little broad, might be a little, depending on the thickness and things like that. So, and then we put these on the floor, and some people would think that looks really cool, to be at a 3, an NRC of 3 at, but again, first of all, most people aren't doing this, and you could swap it for the ceiling, I guess, but it's such a tight cue that it becomes almost inefficient in a sense, despite the fact that it looks more efficient than anything. Then we started separating them, and again, a lot of this too also had the spacing of them and various things like that. Once we started doing some spacing, we started to get some decent results out of it. Now, this was a tight one. This particular one is at 80 hertz. So this is a 4-inch device, 4-inch thick device at 80 hertz. And that we felt was where we wanted to be. And you see, there's not too much information above that. I mean, it tapers down to, 250, and then there's nothing. And that's really what it should look like. All those other anomalies that we saw in the previous test had to do with, the closeness to the units, the effects that were happening to them. This is much more reliable in terms of what what we came up with. And again, going from, this, the test units mounted together as in corners, that's what happens. You look at, the left side, you can see all these different anomalies have to do with the way that they're mounted and the way that they're put together. As we started to separate the units, we started to get more, number one, it showed the more of the efficiencies of it, but two, it showed, like that one spike from 31.5 to 25 hertz is just an anomaly of the lab itself. That really, we don't take that one seriously, but the rest of it was pretty good. And that's what we want to see. That's the kind of response that we want to see. And, as we got closer to it and in different types of traps and stuff like that, we started to get more of this type of response where, we really are looking at a 1.8 is a great, great amount of energy being absorbed. And it's, in the modal field, that's awesome. And again, we can control that depending on the size of the unit and things like that. And here we have, the corner module, and you'll notice that it's broader band. We're showing, effectiveness from 50 to 100 hertz with just a little bit of a drop, not significant. And then it tapers off very quickly. And so for, something like that, and we can do that in a flat trap or, a corner trap as well. It's easier in a corner trap, but it's gives you some ideas of some types of things we can do. And again, depending on the diaphragms, the damping, and various other units, we can change that to to create what a customer wants. I say we, I don't own the company anymore, but so I always speak that way. Again, pointing out low frequencies are pressures more than just waves. And they have a focused response, and remembering that NRC is not a 0 to 1 scale and never has been. So, and this is more information just about the test itself, and that's pretty much it.
That's a great presentation, Richard. And I think, like there's always a confusion around the NRC and the absorption coefficients because of the way that we are taught in school about mechanics, that for any coefficient scale, the one is the asymptotic limit of how high it goes. So
Yeah.
I just could never. That is one of the major things that like you'll find me sometimes arguing about lab tests and all because again, I just couldn't wrap my head around the fact that we get so much deviations in lab tested results of same products through different labs, and some are
Yeah.
not even able to test above one. So I've never really personally paid much attention to how it works. So what is the actual constraint here? Is it because the labs are actually considering one as the asymptotic limit, or is it because they can't measure it that deep to be able to derive coefficients higher than one?
Well, let's put it this way: when we talk about reverb chambers, and we talk about when Sabine started this, 130 years ago, or 125 years ago. Um, in 2023, if you ever want an interesting article to read, read Physics Today, the 2023, I think it was the April issue, and scientists out of actually scientists from both the United States and Germany um, wrote this paper and really gave the whole story of how it began and where it is today. And ultimately, if you read the end of the article, they say, well, it still doesn't work as good as it should, but it's what we have. And frankly, in 2023, this was 2024, and I'm not only shocked but kind of disappointed that we would accept that. That we would accept that. This kind of this kind of crazy acceptance of something, and I see this all the time. I see it in the meetings, and it's like, and I don't know if you know that in ISO 354 has been pretty much abandoned by ISO, and it's like a ASTM C423. It's been abandoned simply because they can't figure out how to correct it. They can't figure out how to make it right. I mean, I'm in the process this summer of working on in my room, and I have a 6,600 square foot building that's in behind my home, believe it or not, because I used to manufacture out of here. But that I'm doing some test, and frankly, I want to rate it in decibels. I don't want to rate it in this. You and I have talked about this. I make the comment all the time. I think it's so ridiculous that the Audio Engineering Society and the Acoustical Society of America don't speak the same language. It's like one talks in noise reduction coefficients, the other one talks in dB. Well, dB wasn't around when basically the concept of that wasn't really around when Sabine was doing his thing. And it's like, but we live in a different world now. And all the test equipment that we use, what does it use as its basic form? Decibels. So, why would I not want, and when we talk about, something, I would love to know, and I would love other people to know that, if you put up a 2-inch panel on a wall, I would like to know what its decibel reduction is at what frequencies. That seems, because you're hitting it with speakers that are rated in decibels. You're hitting everything in it is, and it's kind of like a personal peeve to me. But again, I come from that world. I come from the world of everything is decibels. So why would we want to? Nobody really understands noise reduction coefficients, no matter how much they think they do. It's this
Yeah,
coefficient concept.
not as standardized as they think they are. I mean, otherwise, why would different labs produce different results?
Well, and you find manufacturers, this always, made me nuts, is that, that you find different manufacturers going to labs that actually test a little bit better because, their equipment either isn't as good or something, who knows what, I hate to say that, but it's like, it's a false narrative. There's so many false narratives that happen with that. And that's why I built my own lab, is just for experimentation. I never used it for our data, because I would use Ron's lab or use somebody else's lab, simply because I didn't want to be responsible for creating information that would be biased. in my case. So, and that's just who I am. But it's one of those things where I'm looking at it now from a standpoint of saying, okay, let's try to communicate in the same way that the rest of the world communicates. And I think it's worth it, and to me, it's going to have to be a free field test, because anytime you're putting it in a room, you are now subject to how big is that room. If somebody has a smaller reverb chamber, because the other problem that's always existed is that there was never a defined, a reverb chamber, honestly, between all of the entities, whether it be ISO or ASTM or whatever, should be the same size. Should be the same size, same equipment, same everything. If you're going to make it a diffuse field and you have, diffusers on the sides, what are those diffusers? How are they placed? If everybody had it exactly the same, then we wouldn't be having this conversation about, labs, and I know, I mean, I sit on the C423 committee for it, and, and it never gets fixed, never. And it's never going to get fixed because you have all these people that have all these sizes of labs, and and different criteria, different products. I mean, different test methodology, not methodology so much, but they have just test equipment. Different microphones. I mean, all of those things make a difference.
Exactly.
In terms of how it's going to perform. And so, consequently, it's like, we drive each other nuts. We drive ourselves nuts trying to compare apples to oranges all the time. And it's never going to change. 100 years, 100 years, and it still hasn't changed. So it's one of my greatest frustrations in our industry.
This is something I've always argued as well. People would respond with that this was the testing done in free field, or this was the testing done in diffuse field. And I've always asked, how much free is this field, or how much diffuse is this field? It's important to have the data about, like, just post up an impulse response of the test room. That gives a lot of context to, like, when you say free field, those anechoic chambers are not even, most of the anechoic chambers out there which are used for testing are not anechoic below 80 hertz or 70 hertz. This resonance is lingering around.
Yeah.
So you can't really call it free field. It's a limited free field. Yet
Yeah.
you end up there.
Yeah, and I think there's always going to be, and when I talk about free field, I'm really talking about, and again, I'll point out something like when I was in the speaker business and making speakers and buying speakers from people, things like that. I always go back to there was a company, and I think they still exist, called Community, that made these big horns. I mean, huge horns, and fiberglass stuff and all that. And they tested their speakers in the back of their factory, and they'd shoot 200 feet and test this thing. That's a true free field. I mean, it was there was nothing blocking anything. It was no, and that's when I talk about a free field. That's a free field. It's really hard to do it. You have to be either outside or else you have a room. But with impulse responses, we can take even a decent sized room and pretty much extract all the rest of what's going to come back, because as long as it comes back before any secondary reflections, then we got a free field. It's fine. And that's really my premise behind this, is to have a free field test that could be done in a reasonable sized room. And have, you have to design the way that it's done properly so that it's, there aren't any other anomalies that happen to it. But we're talking about something that's coming back in milliseconds and giving us X amount of information, and that information is going to be pretty static, pretty consistent from room to room to room, as long as there's not other noises or anything like that going on. And that to me seems to make a lot more sense than anything else. It's a way for us to now correct, and to have it decibel based. I mean, like I said, I if I had a nickel for every company I've seen, I shouldn't say it. I've seen several companies over the years tout that a 0 to 1 is a 0 to 100%. So that a 1 means it's 100% absorptive, when in fact a 1 is somewhere around 6 to 7 dB. That's not 100% in anybody's book. So how do you mitigate this false information from getting around and people thinking that? And I guarantee that most guys in the acoustics industry, not in the acoustics industries, but in the sound industry, who are dealing with acoustics and don't understand, they say, well, now if I put up this 2-inch panel, it's reaching a 1 at 300 hertz and it's going out to 6K. That's perfect absorption. No, it's not perfect absorption. It's not even close to perfect absorption. And you can't, and they get disappointed. Same thing. And as well as I do, every acoustician I know, and I know a lot of them, every acoustician I know goes by his experience, his or her experience, not by the data, when it's coming to common products. And the reason they do that is because experience has taught them what it really does do, whatever that product might be. And really, it shouldn't be that way. We should have the ability to have data that gives us, a solid information that isn't misconstrued or given in a manner that makes you turn your head and go, I'm not so sure about that. So anyway, I'm preaching now, so forgive me.
No, but that totally makes sense. Actually does. I mean, keep going for this fight of change in standards. You have all my backing, even if it means nothing.
Thanks, I appreciate
I'm
that.
all in for it. That there's a need to just improve these standards. There's the high need for it.
Yeah,
Let me
exactly.
just start with the questions. We have a few right now. Yeah.
Okay.
So Andy, while asked, is there any difference implementing the diaphragmatic absorber at particular boundaries? Example, at the front speaker end versus side wall versus rear wall versus ceiling.
Well, like I said, it really, let's take the turn. You had a comment that you wanted answered about like a mastering room, and you look at speakers. A lot of times there is a significant amount of low frequency information coming out of the back of a speaker, or it wraps around, which it does that as well. And there is definitely some efficacy to having a bass trap in the back in that particular case. If it's causing a problem, if you've got this, because that's going to give you misinformation if you're listening to that. And not only that, it's going to be slightly delayed as well. So that, that becomes a problem. So you want to absorb that energy as much as possible. That's a place, honestly, that I wouldn't use a diaphragmatic absorber. For me, if I was looking at the back of a mastering room or a control room, not so much a control room because they don't typically have that problem, but in a mastering room, I would probably put a really serious velocity based absorber behind there, just to get rid of any energy coming back from that space. Now there's going to be those who disagree with me, but that's just based on my experience as an engineer. The putting them on the sides can make sense to some extent if they're close to the corners, because it's going to be a reflection zone that comes in there, and it can take care of some of that information. Or like that room, that crazy room I told you about with all the subwoofers with them facing sideways, and sometimes they do that. Sometimes especially I found guys that are doing video rooms, these home theaters and things like that. If they are in a position where they're putting subwoofers on the sides, it might also be beneficial because now you've got this cross happening, it might be beneficial to have bass traps capturing the secondary reflection, coming through. So, there's always going to be situations where, that can make sense. And most people are smart enough, most guys that are doing designs are smart enough to look at that and say, yeah, that might be a good application for this, because I have all this energy that's coming in sideways. I need to put, some bass trapping in there so that it doesn't do this. That's what you want to avoid. You don't want it bouncing back and forth all the time, because, and often these are frequency ranges that, 20 to 40 hertz is nothing. I mean, they're very low frequency stuff, and it's and they need to control it better. So yes, I can see applications where, in many cases where that might be applicable. But like I said, for me, I'm always going to look at where the source is. The source determines in most cases where the first reflection needs to be controlled, and that's that's going to be, you kind of think about it that way. That's going to be your best bet in that. So.
Yeah, that makes sense. And just to add a bit to it, there are 1,000 ways that different devices can be used in different ways, and membranes can be used in different ways depending on who's using it. For example, for a long time, I was just inside this bracket when I used to think that membranes are only used for targeting very narrow problems. That if I have a resonance at 54 hertz, I'll just tune it perfectly to 54 hertz and only then I can use it. And I used to do that for a very long time.
Sure.
And then I got in touch with you just recently, but I saw your researches way back, and that's what this was the first time that I realized, okay, that rigid membranes can be really broadband too. And same goes for Helmholtz. A lot of people still think that Helmholtz are just very targeted absorbers, and in many ways they are, yes. But you can also increase their Q factor by compromising a bit on the amplitude absorption, how much they absorb, and get them work for fairly broadband as well. So it just really depends designer to designer, design targets, design
Sure.
goals, and the room. Same goes for fiber as well. Um, I mean, everything can be used for everything. If you use a rigid insulation, that can have a membrane function as well. I don't know, Richard, if you've tested that or experienced that, but in some of designs, we found that very rigid boards, very high density boards, can have a membrane-like action sometimes when mounted in that way.
Sure. Yeah, absolutely. That's and I've made Helmholtz. I haven't. It's funny. But Helmholtz was really popular about 10 years ago. I did one for the Boston Symphony studios, and that was a John Stork design, and it worked very well. He knew that where his problem was going to be. He put it in the right place. And it was quite a bit of it, but and it was it was this kind of frequency, problem. And he, but he knew what it was, and John's, smart enough and good enough that he knew exactly what he needed to have. And so I've done Helmholtz for that, and you can make dual hole Helmholtz. There's various ways to get a little bit more out of it, but it is typically a pretty tight frequency. So that's its downside, I guess, for lack of a better word. And its performance, if you look at the, but again, I say this with caution, because I have never tested Helmholtz in the modal zone. So, and to really understand its actual performance, we would need to do that. We would need to test it in that modal zone, and where it's used, where it's actually in being used. It's always been tested in the in the diffuse field, and the diffuse field, by record, whether you look at 354 or 423, by record, is not supposed to be below 125 hertz. So and some even don't actually do sweeps till about 100 hertz they start. So you really can't get that out of a lot of labs anyway. So it's that's a whole nother study, interesting one that could be done to see exactly what they're doing. I know they're not as efficient as diaphragmatics. There's no question about that. But
There's
but
only one time I use hell modes, and just once in my entire career, and that was like uh, when I thought that's the only option I have. There's a huge problem with hill modes with re-radiation and residual resonances,
yeah,
huge re-radiations, and it becomes even more difficult to contain them because unlike diaphragmatics, hill modes are really affected by what's in front of them. If you put
no,
a massive insulation block, it's just not going to work
no,
because it's working with the uh, actual air fluctuation principles, not just vibration fluctuations.
yeah.
So yeah, but that's a very interesting. I mean, I learned a lot through that project. Still looking forward to.
Yeah, it's an interesting. It's funny you bring it up because I really haven't thought about it for a long time. But Helmholtz does work. I mean, and we make, RealAcoustix makes a lot of products that are based on holes, that are for broadband absorption. Now, it's not super broadband, but it's, within, we find it a lot, when you look at, might see these kinds of products for offices or for, student rooms and things like that, where, they're putting holes in a 2x2 drop down, situation. And if put with insulation on the back, they work pretty well right in the voice range. It's if the whole pattern is correct and stuff like that. That's one thing about Helmholtz is you can control where its frequency band is simply by the size of the holes and the all of that stuff and the spacing and all that. So it's an interesting, but I tend to find that it's really finite in most cases.
Yeah,
It's not broadband enough for my taste, in perfect use. So, but I understand, yeah, I hadn't even thought about that in years. The Boston job was 10 years ago, and oh yeah, I did that once. So I did it a couple of times for him, and it was interesting.
yeah. I never thought I would ever use a helm modes, and I still don't wish that I would ever need to use a helm modes. They are just crazy difficult to work with.
Yeah, yeah, it is. It's like I said, I think that and the amount of as we say in the United States, the bang for the buck is not that great with Helmholtz. You don't get as much performance out of it as you'd like to for what
Hmm.
for the difficulty that it is.
Yeah.
So it's
It's
good.
a question by Murray. From the Eigen mode view, it would suggest that we need traps at each harmonic of the room dimension. I think he asked that while you were presenting that Eigen mode slide.
Yeah, I mean, that's I understand that concept, but again, that's most of that is what you're seeing is based on the specific frequencies, and it's not taking into account the way that a C423 test is done, because we still use the same principles, because the C423 is a constant signal done for 20 seconds and give or take, and it's and that it basically excites the whole room. The eigen mode is really based on more of an impulse response, so it's going to be at any given point. Whereas with the way that a C423 is done, the only probably great side about it is the fact that it is exciting the entire room for a long period of time, and you're looking at the decay rate of it. So there's that part, I think, is pretty good for assuming that we're not missing anything. Those are those points that you see at the various frequencies would only be an impulse. Yeah, and that's whereas, like I said, in the test, excuse me, in the test, it really is because it's a long decay that you're testing. You really are getting it's swimming all over the whole room. That's the whole point behind it, is that you're creating this big field of noise. This isn't an impulse response. Now, there are some people that have been experimenting for several years with using impulse responses for C423 or something like that. But the downside of it is that you're not looking at a long-term field of sound as you are with the C423 the way it is. That's why I didn't mind doing it the way it was, because even for low frequencies, it's going to tell us a lot.
I hope that answers the question, Ade. And we have a question from Colin. What is the lowest frequency that can be achieved at these absorption numbers? I think that was also asked during the presentation of testing. I should have asked this earlier too.
Yeah, the lowest that we've gone with it was 40 hertz. However, I don't know that there's a limit. It'd be interesting. At some point, the depth of the unit really determines, how it's going to perform, and the depth and obviously all the interior things that we're using, the damping materials and things like that. They all react together, and we didn't go below 40 because nobody ever wants it. I've had one customer in 18 years ask for 20 hertz, and I said, well, we haven't tested it. We could do that, but it'd be a one-off. It's a very rare need that somebody has to get down below 40 hertz. So we got down to 40, and I felt very comfortable that would cover 99% of the customers that would be looking for something. Most of the problems that I've ever seen fall between 50 and 70. It just seems to be those, because the rooms aren't that big. If you were talking about a huge room, but I think when at some point in time, like I was telling you about, I did a project one time for Planet Hollywood in Las Vegas, and they have a theater. It's a 7,000 seat theater there. It's they do rock concerts and all kinds of different things there, and I used to actually be the engineer for that room back when I was a young man, and I was the sound engineer for it. So it was fun to do this for me because we did this whole a lot of it, and the majority of it was just 2-inch panels that were really highly designed and stuff like that. But he wanted to have some bass trapping, and they have these huge 4-foot beams holding up the second floor throughout the first floor. And we did literally, it wasn't anything diaphragmatic at all. This was just, capturing as much energy as we could, and ended up working really well. They were round columns, so we were able to capture it both coming in and coming back from the wall. And so, you look at those kinds of, and we were able to capture quite a bit of energy, and it was very broadband. But, we were almost a foot deep in material. It was fiberglass and various other things. Those, and that's so you treat a concert hall differently than you would treat a studio or something like that, because you're really just you're just trying to get it not to talk back to you. It's the last thing an artist wants to hear is his reflection coming back on him. So it's that's doing a live room is very different than doing a studio. So
yeah, I hope that answers your question, Colin. Great answer for me. And before I answer the further questions, guys, if you have any more questions, please just type down in the comments, chat in the chat. Or also, we were actually planning to show you guys some case studies. If you guys are still hooked and want to see that, but already the session is stretched too long. So just let us know in the chat if you guys would like to see a case study. Maybe Richard can pull something up, or if you have any more questions, we'll just wrap it up with a Q&A.
Yeah, I could probably do something I wasn't really prepared to do a case study per se, other than
Okay.
And I think what we should do is maybe, it's late no matter where you're at. So
Okay, late for you.
late in the morning or late in the evening. It's it's only 12:30 in the morning here, but I think what we should do is maybe take a look at doing another one, in the
Yeah,
future.
sure. I think it's already stretched too long. Let's just take a couple of questions and wrap it up, I guess, right?
Yeah, no problem. No problem. It's fine.
Cool. So we have James asking, is there a metric like RT60 that is valid in a small room?
Yeah, I mean, it's wow, there's a good question. I mean, when you're testing, for an RT60, you could do a smart RT60 is kind of tough in a small room. It's because there just isn't enough of a time factor. Again, using an impulse response in a system like Smart, which happens to be one of my favorite ones, but REW, which is a free and really pretty good program. Doing something like that, just doing a quick impulse response can give you some of the same information that an RT60 will give you, and maybe more, depending on how you analyze that impulse response, the sweep, and what kind of sweep you're using, and that it's so yeah, I think those in a small room can be very beneficial. And I know you talked about, you were talking about wanting to look at plots, certain plots, and those can be beneficial as well, to looking at what, where your problems might be, and what they are, and that kind of stuff. But yeah, I think that's, I love the fact that we live in the time that we live, and that there are, so many different programs, and you don't even have to spend a fortune on them anymore. It's there's just a lot of things out there that did not exist when I was young. When I was an engineer and stuff, we were still using third octave analyzers, and trying to tune a room that way and stuff like that. So it's great now.
Yeah, basically, if you're using REW or anything, as an alternative for RT60, you can just see the impulse response on the ETC curve. The decay is pretty much clear in these graphs. But if you just start seeing the RT60 graphs, these are basically computed graphs. These are not measured values there. So every time you measure the same room at the same position, it's not uncommon to see erratically different curves on the RT60 graph, because it's just a computed value, and diffuse field doesn't exist in small rooms. So it just computes anything it wants to. So just take a look at the impulse response on the ETC curve.
Right. Yeah. There's a lot of better ways than the RT60 to accomplish that. I think we used RT60 primarily to see how much delay time we had in the room and things like that. So it's things have come a lot. Waterfalls and things like that can tell us a whole lot more about what a room's doing.
Yeah. Colin mentioned waterfall graphs. Yeah, they're good graphs too. They show a lot.
Yeah, they do. Yeah.
Coming to Colin's question, what are the approaches to using these types of absorbers? I think he's referring to membranes only, to control SBIR.
Don't really know. I don't think we've ever looked at it from that standpoint, or that I've ever looked at it from that standpoint. I'd have to see. I'd really have to think about that one. I don't know.
I share the same view, actually. I mean, SBIR responses, except for the front wall ones, are mostly in the higher domains, which can be controlled by just insulation, broadband absorption.
Right.
So I don't see why would you use membranes for something as high in frequency as a simple SBIR response. For front walls, they can sometimes be used, but there are simpler ways to do it. So again, not really beneficial, but yeah, we have sometimes done it, and it's not very efficient.
Yeah, it's like I said, I don't think I've ever thought about it in that frequency range that we're talking about. So it's I'd have to do some research on that, and to think about whether or not that was feasible, as it were.
Yeah, and that wraps us up with all the questions. Thank you guys for attending, and here's a future seminar suggestion: learning how to best analyze impulse responses. Yeah, that's actually a good one. That's a good time to start bugging Richard for another session as well. It took me 6 months to convince him for one.
That's okay. It's been good.
Thank you so much for Richard. It was really amazing, and I'm looking forward to talk to you again.
Well, yeah, same here, and I look forward to it. And thanks everybody for joining. It was fun. Enjoyed the questions. It was nice. So we'll look forward to the future. Okay.
Looking forward. See you again, Richard. See you again, guys. Hoping in for another webinar, and start bugging Richard, just like I said.
Bye to the world.
Take care, guys. Bye bye.